I will go to the fifth and last lecture of week 8 of this course, and in this week you have learnt about Miller indices and about reciprocal lattice, Bragg's law and X-ray diffraction. Okay. We will continue discussing X-ray diffraction in more detail in the next week, okay. But we will review what we learnt this week and then do some practice problems based on the contents of this week in today's lecture. So, week 8 lecture 5 will be review of week 8 and practice problem. Let us first review what we learnt. So, in this week we learnt Miller indices, reciprocal lattice and X-ray diffraction. So, we learnt how to represent a plane, how to represent a normal vector. We learnt the concept of lattice planes and Miller indices for directions, surfaces, families of planes, distance between planes, and we also showed how to calculate the distance between planes. Then we learnt about X-ray diffraction, Bragg scattering law, we learnt about the reciprocal lattice and some details about the instrumentation of for the X-ray diffractometer. Okay. So, now let us do a couple of practice problems. Okay. So, the first problem asks what are the reciprocal lattices for simple cubic, body centered cubic and face centered cubic lattices. Okay. So, to do this what we need to identify is, okay, so let us first take the simple cubic. So, A1 is equal to A times I. Okay. So, if A is the side of the cube, then so clearly you have, okay, so this side is A. So, A1 is A times I, A2 equal to A times J, A3 equal to A times K. So, what do we get? So first thing let us calculate A1 dot A2 cross A3. Okay. So, now we can do this quite easily. So, A1 is just A times I dotted into, now A2 is A times J and A3 is A times K. So, A2 cross A3 can be written as A square multiplied by I cross J. Oh, sorry, not I cross J, it should be J cross K, should be J cross K. Okay. Now, J cross K is nothing but I. Okay. So, you have so J cross K is I. So, this is A I dotted into A square I. This is equal to A cube, okay, which is the volume of the cell. Okay. So, you can verify that the volume of the cell is given by this. Okay. And now, so since we know all these cross products, so A2 cross A3 is A1, okay, A2 cross A3 is A1, A2 cross A3 is A square I. Okay. So, then what you can show is that B1 is equal to 2 pi A1 cross A2 cross A3 divided by A cube. Okay. So, this is equal to 2 pi A2 cross A3 is A square I by A cube, which is equal to 2 pi by A I. Okay. Which is what we showed a lot earlier, which is what we showed right when we talked about reciprocal lattice. Similarly, you can show that B2 will be 2 pi by A, times j and B3 equal to 2 pi times k. Okay. Now, so this completes the reciprocal lattice for the simple cubic, and you can see that the only difference between the simple cubic lattice and the reciprocal cubic lattice is that instead of a that you had in the case of simple cubic lattice, you have 2 pi by a. Okay. So, the reciprocal lattice is a simple cubic lattice of size cubic lattice of size 2 pi by a. Okay. So, that is the reciprocal lattice of a simple cubic lattice. Okay. So, now next let us go to face centered cube. Okay. Let us go to FCC. Now, in FCC your primitive translation vectors are the following. Okay. So, let me draw the FCC cell. Okay. So, I can take this and this as my primitive translation vectors. Okay. And so I can take A1 equal to, and if this side is A, okay, then A1 equal to A by 2 times I, or I will take it as j plus k, A2 is equal to A by 2 I plus k, and A3 to I plus j. I can take them in any order, it does not matter. Okay. So, these are my 3 primitive translation vectors. Okay. Now, you can directly guess what the volume will be. Okay. The volume of the volume that is formed by these 3 primitive translation vectors, but let us work it out. Okay. So, so A2 cross A3 is equal to, so A by 4. Now, I cross I is 0, I cross j is k, okay, plus now k cross I is j, k cross j is minus I. Okay, k cross j is minus I, and now if I take A1 dot A2 cross A3, this will be A by 8 times. Now, you will have a term j dot j and k dot a, there is no I term. So, you will get 1 plus 1 is equal to A by 4, which is what you expected. You would expect the volume to be 1/4 that of this cube. Okay. So, now, so what do we get? We get B1 is equal to, now you already have A2 cross A3. So, that has a factor of A by 4, and the denominator will also have A by 4. So, it should be A square by 4, A cube by 8. I forgot the a cube by 8 and a cube by 4. Okay, so, B 1 will be equal to 2 pi by a k plus j minus I, okay. And B 2 by a, and again you can just do it by permutation. So, you will have for B 2 you will have I plus k minus j, and for B 3 I plus j minus k. So, you can see by this, okay. So, what do these vectors look like? So, what these vectors look like? So, if you take k and let me take this as x, this as y, and this as z axis. Okay. So, k plus j minus I will look like a vector, okay, that okay. So, that is along the diagonal of the cube, okay, but it basically goes along the diagonal of the cube from one corner to the opposite corner, okay. Similarly, the others, so this is clearly along the body diagonal, okay. So, similarly all these will be along body diagonals, okay. So, this basically says that all reciprocal lattice vectors are along body diagonals, okay. This implies reciprocal lattice is BCC, okay. So, the reciprocal lattice of FCC is BCC, okay, is a BCC lattice, and interestingly this also leads to the result that this implies that reciprocal lattice of BCC should be an FCC, okay. So, by solving the reciprocal lattice of the FCC, we have also solved the reciprocal lattice of BCC, because the reciprocal lattice of a reciprocal lattice is the original lattice, okay. So, the reciprocal lattice, since the reciprocal lattice of BCC is FCC, it follows that the reciprocal lattice is, since the reciprocal lattice of FCC is a BCC, it follows that the reciprocal lattice of BCC has to be FCC, okay. So, basically there is this real lattice reciprocal lattice pair between BCC and FCC. So, FCC forms this real and reciprocal lattice pair, okay. So, if the real lattice is BCC, if the Bravais lattice is BCC, then the reciprocal lattice will be FCC. Similarly, if the Bravais lattice is FCC, the reciprocal lattice will be BCC, okay. So, next problem is a rather simple problem. What is the angle between the Miller planes 120 and 471? So, we go back to the definition of the Miller indices. So, HKL, okay, are their reciprocal of intercepts, okay. So, they are proportional to the reciprocal of the intercepts, okay. Therefore, the normal vectors to these planes to HKL is equal to HI plus KJ plus LK divided by square root of H square plus K square plus L square. That is the unit normal vector to the plane HKL. Okay. And the angle between two planes is equal to angle between normals. So, what it immediately follows is that if you want to find the angle between these two planes, okay, so for the normal vector for the 1 2 0 plane is equal to I plus 2j divided by square root of 5, and the normal vector for the 4 7 1 Miller planes, okay, that is 4I plus 7j plus k divided by 4 square is 16, 7 square is 49, and 1 square is 1. So, 50, 66. Okay. So, we have these two normal vectors. Now, we just have to find the angle between these two, and since these are unit normal vectors, so the angle between them is just the dot product. So, cos of angle between them is equal to n 1 2 0 dotted into n 4 7 1. So, that is nothing but the cosine of the angle between them, since they are unit normal vectors. So, we can do this easily. So, if you take the dot product, you have I into 4I, and then you have 2j into 7j. So, those are the two terms that will contribute. So, cos theta is equal to I into 4I, that is 4 plus 2 into 7 14 divided by square root of 5 into square root of 66. Okay. That is 1 into 4 4 plus 2 into 7 14. So, that is the dot product, and then divided by this square root of 5 into square root of 66. Okay. So, that is sorry 18. Now 18 square is actually 324. Okay. So, it is actually very close to 1. So, you see that so theta is very small. So, theta equal to cos inverse, this is almost about 0.98. So, this is the answer, this is the angle between the planes. So, So, the angle between the planes is cos inverse of this will be very close to 0 degrees. Okay. So, so the angle between the planes is extremely close to 0 degrees. Okay. So, I mean you can find the numerical value of you can find the exact numerical value, but I will not bother doing that here. Okay. But I have illustrated how to calculate the angle between Miller planes. So, with this I conclude the 8th week of this course, and in the next week we will continue discussing more details about X-ray diffraction, okay, and we will look at how to actually how to analyze the X-ray diffraction pattern. Okay. Thank you.